Okay, in this video, we're going to talk about conditional probability with equally likely outcomes. Here, we have the formula, which is the probability of event E occurring given that F has occurred. So, in these problems, we're told that F has occurred. Okay, so the numerator is going to be the number of ways that E and F can occur at the same time. Since we were told that F occurs, we don't have to divide by the sample space, we just divide by F since we're told that F has occurred. So, what is the number of ways that E and F can occur at the same time over the number of ways F can occur, since we're told that F has occurred. Now, sometimes this is 0. Sometimes the number of ways that E and F can occur is 0. We usually look at examples where it's not 0, but it most certainly could be. If F has occurred, maybe E can't occur. So you may find examples like that on your homework where it's 0, but usually we look at cases where it's not 0 because that's a little bit more interesting. Okay, so here we see the definition, the probability of event E given that event F has occurred, and this is denoted P of E given F. This vertical line is the given sign there. Okay, let's look at an example. So a team consists of 8 Australians, including Edna, and 5 New Zealanders, including Stephen. A team must select 2 members to serve as officers, one as a spokesperson and one as a chairperson. What is the probability that Edna is the chairperson given Stephen is the spokesperson? Okay. So there's a lot of different homework and examples of that are very similar to this. You may have different scenarios or that type of thing, but this is a very common type of question. Okay, so in the question, it breaks up people into groups, and in this question, it's 8 Australians, and this includes Edna. Okay. And we also have 5 New Zealanders. So I'm going to write them as NZ. And this includes Steve. Okay. That includes Steve. So Steve is one of the 5. Edna is one of the 8. Okay. Now, the question is, what is the probability that Edna is the chairperson given that Steve is the spokesperson? So, one thing to notice is that we are talking about specific roles, specific offices, specific positions that these people are taking. Okay, so this would not be a good combination problem because these people are taking specific roles. That is to say, that Edna being the spokesperson is different than Edna being the chairperson, okay? Or you might know being the CEO of a business is different than not being the CEO or working another job, right? So when people take specific roles, order matters. So if order matters, then we're going to need to use either multiplication principle or permutation. Um, if it didn't matter, we would use combinations, but by the phrasing of this, it is going to matter. Okay, so how do we do this? Well, we need to find the number of ways that Edna can be the chairperson and Steve can be the spokesperson. I'm going to show this through multiplication principle, but you can do it other ways as well. But I think it'd be easiest to see through multiplication principle. So say that this is the chair, and say that this is the spokesperson, and we have, for the numerator, we are saying that Edna is the chair. So that's only one choice. And we're saying that Steve we're guaranteed that Steve is the spokesperson, and that's only one choice. So that's just 1 times 1 amount of ways that that can occur. There's only one way that that can occur, that Edna is the chairperson and Steve is the spokesperson. But the denominator is that Steve is the spokesperson. So there's a few ways that that can happen, right? So one of them is that you could have, I'm going to draw that a little bit different. For the chair and the spokesperson, well, we know that we're told that Steve is the spokesperson, so we can just let that go. But how many people could be the chairperson? How many people could be the chairperson? Now, Edna, the specific event is that Edna is the chairperson, but how many people could be in the chair totally if Steve is the spokesperson? Well, how many people do we have? We have 8 and 5, that makes 13. Steve sat down as the spokesperson, so we must have 12. Okay. So 1 times 1 is just 1, and 12 times 1 is 12. So I believe this is a 1/12 chance that this would occur. Okay, so this is how we can break it down, and this is how you can break it down with, multiplication principle, which is much easier to see for these types of problems. Okay, I have another example here. So same setup, 8 Australians, including Edna, 5 New Zealanders, including Stephen. And we're still selecting 2 members, 1 to serve as spokesperson, 1 to serve as chairperson. What is the probability that Edna is the chair, given that Stephen is not the spokesperson? So this is a little bit different. It's just kind of a new twist on the same problem. And I'm going to set it up the same way. And I'm going to solve it in a very similar way. Okay. So the only thing we're guaranteed in this problem is that Steve is not the spokesperson. Okay. Well, for the numerator, we're saying that Edna is chair. So that's only one choice. There's 13 total people. Edna sits down, right? Edna sits down here. And so then we're down to 12, but Stephen can't sit here because we're guaranteed that that didn't happen. So then we'd be down to 11. Okay. Now, what's the total amount of things that can happen with Steve just not being the spokesperson? Okay. So Steve not being the spokesperson, then there's 12 people that could be there. Okay. 12 people. There's 13 total in my problem here. And so Steve didn't sit here, so there's 12. And then for the chair, there's the 11 other people and Steve. So that would be another 12. Okay. So I think the denominator would be 12 times 12. And I think that the numerator will be 1 times 11. So I think that this is going to equal 11 144. Okay. That's how I would break that up. All right. I think I have one more example. Yeah. One more example of this type of problem. Same setup. We have 8 Australians, including Edna, 5 New Zealanders, including Stephen. We're still picking 1 spokesperson, and we're still picking 1 chairperson. But what is the probability that both offices are New Zealanders, given that they're both from the same country? Okay, so in this breakup, we're not really concerned with Edna and Steve specifically. Now we're just concerned with country, okay? What is the probability that both are from New Zealand, given they're from the same country? So really, we're just breaking it up by country at this time. Okay. So I can still use that multiplication principle to break this up. So this would still be the chairperson, and this would still be the spokesperson. Okay, and for the numerator, well, it would be how many ways can they both be from um, New Zealand if they're from the same country? Well, that's redundant. If they're both from New Zealand, then they're both from the same country. So it's just how many ways can they be from New Zealand? And that would be 5 times 4. There's 5 choices for the first one, 4 choices for the second one. Someone sits down, so there's 4 choices. And so that's 5 times 4, and that's 20 up top. Okay. Then it's how many ways can they be from the same country? The same country. So that's going to be 2 different ways because in this problem, there's 2 different countries. So 5 times 4 is in the sample space, of course. That's New Zealand. And then 8 times 7 would also be in the sample space because that would be that they're both from Australia. And that is also a possibility. Okay, so it looks like we're going to have 20 over 20 plus 56, and that's 20 over 76, and that would be 5/19. Okay. Well, I hope this helps. I hope this gives you at least kind of a jump start on understanding these types of problems. And yeah, just let me know if you have any further questions.